It was important to understand the formulation of the aggregation and transformation method that is used to update node embeddings in graph neural networks. And it was also important to get an intuition of how this is performed in matrix form. We are now ready to turn our attention to graph attention networks. Here's the fundamental intuition behind graph attention networks. If you look at a particular graph, and if you look at the neighbors of each node in the graph, all of the neighboring nodes may not be equally important for a particular target node. For example, if you look at node 2, it's connected to nodes 1, 3, 4, and 5, but every connection may not be equally important. There might be certain connections that are stronger and other connections that are weaker, so the connection to each neighbor might have a different importance score. Remember, when we use graph neural networks, node embeddings are generated for each node, and we use those node embeddings to perform predictions. The predictions can be node classification, link prediction, or graph classification, or something else. This idea of attention was originally introduced in the field of natural language processing back in 2017 with the transformer architecture for NLP. Attention in NLP is a mechanism that allows models to focus on specific parts of the input sequence. The input sequence is typically a sentence, then generating each word of the output sequence. Attention dynamically weighs the importance of different words in the input, allowing the model to handle very long-range dependencies more effectively. This is very useful in tasks like translation, where the meaning of a word often depends on distant parts of the sentence. This fundamental concept of attention can be applied to graph neural networks, where we assign a different importance score for every connection between a pair of nodes. This attention score is referred to as an attention coefficient. So in addition to aggregating all of the information from the neighboring nodes, we use an additional attention coefficient to weigh the contributions of each neighbor to the current node's embedding. Let's say this attention coefficient is represented using E, so we have a value of E for the connection between 2 and 1, 2 and 3, 2 and 4, and 2 and 5. Here you can see that the connection between nodes 2 and 3 is the most important for node 2. Its attention coefficient value will be higher. Now, when transforming and aggregating the neighboring nodes' embeddings in order to update the embeddings for node 2, the attention coefficients associated with each connection will upweigh the contributions of the more important nodes and downweigh the contributions of the less important nodes. These attention coefficients are also learned parameters, that is, they're determined during the training process of the graph neural network. I'll first do a very high-level overview of how the attention coefficient is computed for each pair of nodes, and we'll dive into more detail in the next video. The formulation that you see here on screen represents how the attention mechanism is used to compute the attention coefficient for each node pair. When you train your graph neural network, you compute the attention coefficient for each pair of neighboring nodes. Here, node I and node J are neighbors. The attention is computed for every such neighboring pair. In order to figure out the attention coefficient, the node embeddings are considered for each node pair I and J. These node embeddings are then transformed by passing them through a neural network layer, the learnable weight matrix. These transformed node embeddings are then passed through an attention mechanism that is responsible for computing the attention coefficient, which is then used in neighborhood aggregation and transformation. This attention mechanism is computed using a neural network with some other specific operations. We'll discuss that shortly.